All right, this packet is just a walkthrough of the second set of notes that I gave you. We started off talking about notation with this packet. X is always going to represent your data value, no matter what type of data you're dealing with. X would be your data value. And then you have your population mean, your population average will be represented by Greek letter mu. Your population standard deviation, which we'll talk about in a second, will be represented by the lowercase sigma, Greek letter sigma, lowercase sigma. And then sigma squared is your population variance. X bar, X with a bar over it, is your sample mean or sample average. Then regular letter S is your sample standard deviation. Then S squared is your sample variance. So notice your notation will change according to whether you're dealing with the population versus your sample. They would expect you to know that once you see this symbolism, this is what you would use when you're dealing with the population, and this is what you would use dealing with the sample. And they don't have to let you know that you're dealing with the population versus sample. They would just give you the symbol that represents it. No matter what, your data value will always be represented by X. Here we also have lowercase n, which represents your sample size. Capital N represents your population size. Mu is your average. Remember, that's adding up all your data values divided by the number of data values. So we have capital sigma, capital Greek letter sigma, that represents the adding up, the summation of your data values. Sigma X is the summation of data values, then divided by the number of data values, which is your population size, or for the sample, lowercase n. Measures of variation. So your range is just your max data value subtracted by your minimum data value. So if we have a data set of 1, 2, 3, 4, we would do 5, which is the largest data value, minus 1, which is our smallest data value, and that would be 4. So this is something we would use to compare groups of data, or data sets. We would talk about the range of data. Standard deviation is a measure of how much a data value deviates away from the mean. If I have the data set of 22, 22, 26, 24, the standard deviation is 1.9. We will look at what that means and how we would use it in a second. This book that we have doesn't talk about or emphasize the calculation of the standard deviation, just the application of the standard deviation. So that's why I told you to find a website, app, calculator, something of that nature that can calculate your standard deviation, something reliable that can calculate the standard deviation. Once again, our book does not focus on the calculation of the standard deviation, but the application of the standard deviation, which is what we'll do in a second. Variance, another way to measure the spread of data, and it's just the standard deviation squared. So make sure, once again, you have something that's reliable that can calculate that. The empirical rule, 68% of the data is within 1 standard deviation of the mean, 95% of the data is within 2 standard deviations of the mean, 99.7% of the data is within 3 standard deviations of the mean. So here's a general representation of those words. We have our mean in the middle. Your normal distribution, the bell-shaped curve, is symmetric about the mean. So that means whatever goes on the right side of your mean goes on the left side of your mean as well. So we have our mean in the middle, 34%, 34%, 13.5, 2.35, 0.15 is on the left, and that same thing is on the right. So 1 standard deviation out. If I add a standard deviation and subtract a standard deviation, that will be 68% of my data. If I do it again, add 2 standard deviations, subtract 2 standard deviations, that will give me 95% of my data. Then go out 1 more standard deviation, that's 99.7% of my data. And then here we have 0.15 and 0.15 on the tails. That'll be 0.3, add that 0.3 to the 99.7, and I have a whole 100% of my data. So all of it adds up to give you 100%. This is just a breakdown according to the empirical rule. So let's put that into action. IQ scores have a bell-shaped curve, bell-shaped distribution with a mean of 100 and standard deviation of 15. What is the percentage of scores between 70 and 130? So what we'll do, what I'm going to do is just go ahead and fill out the whole distribution chart, and then look at the 70 and the 130 and see what percentage is between the two. So we have our mean, which is 100, and our standard deviation is 15. They gave us that. So the right side of my chart, the right side of my normal distribution curve, I will add a standard deviation, 100 plus 15 is 115. Add another one, that's 130. Add another one, that'll be 145. Left side, we'll subtract. Subtract 15 is 85. Subtract 15 again is 70. Subtract 15 one more time is 55. So on the right side, we go out 3 standard deviations. We add 15 3 times. On the left side, we subtract 15 3 times. So we have our mean in the middle, 15 added 3 times, 15 added, subtracted 3 times. Our percentages will stay the same according to the empirical rule. These numbers may change according to what our standard deviation is and what is our mean. So if we look at our 70 and 130, what's in between the two is 95% of our data. So you can either add up these 4 numbers or just remember that if I go 2 standard deviations out, which is what 70 and 130 is, the empirical rule said that they will add up to give us 95% of our data. Measures of relative standing and box plots. We start off with Z-scores, just a standardized value. It gives a standardized way of looking at our data values. It's the number of standard deviations that a given X is above or below the mean. So we'll be able to be more precise with the positioning of our data values in comparison to the mean. Instead of just going 1 standard deviation, 2 or 3 standard deviations, we can go 1.2 or 2.6. We can go negative 3.1 and so on. We can be more precise with the positioning of our data values in reference to the mean. This is how we will calculate it. If it's the population or if it's the sample, it will be calculated the same way, just using different symbols. It's the data value minus the mean over the standard deviation. And we're always going to round our z-scores to 2 decimal places. So once again, the data value minus the mean over the standard deviation. Here we have an example of the Chips Ahoy cookie with 30 chocolate chips is in a bag of 40 cookies with a mean of 24 chocolate chips. So the average cookie has 24 chocolate chips, and the standard deviation is 2.6 chocolate chips. What is the z-score of the cookie? So the cookie in question has 30 chocolate chips, and we want to know what z-score represents this 30 chocolate chips. In the bag of 40 cookies, the average is 24 chocolate chips. So our average is 24. They say our standard deviation is 2.6. And like I said, the data value that we want to convert, the data value in question is 30. The cookie in question is 30. So we do 30 minus 24 over 2.6, and that'll be 2.31. So the z-score will be 2.31. That means it will be 2.31 standard deviations above the mean or above the average. Here's another example. A can of Coke with a weight of 0.8295 pounds is in a case of 36 cans with a mean weight of 0.81682 pounds and standard deviations of 0.00751 pounds. What is the z-score of the can? So once again, this 0.8295, we establish what is the data value in question. That's the data value in question. Then they give us the standard deviation of 0.00751 and the mean of 0.81682. All right, so the 0.8295 is our data value minus the 0.81682, which is the mean, divided by 0.00751, which is standard deviation. So it is 1.69 standard deviations above the mean. All right, ordinary versus unusual values. Values that are greater than 2 standard deviations away from the mean are considered unusual. So my ordinary values will be -2 standard deviations to +2 standard deviations. So we're talking about within 2 standard deviations of the mean, they are considered ordinary values. If you go beyond 2 standard deviations, or whether it be greater or lower or below, they're considered unusual values. So if you go beyond the 2, whether it's positive or negative, they're considered unusual values. All right, so the author of this book measured his pulse rate to be 48 beats per minute. If adult males have a mean pulse rate of 67.3 beats per minute and standard deviation of 10.3 beats per minute, is his pulse rate unusual? So the data value in question, we're looking at 48 beats per minute. They give us the mean 67.3, standard deviation 10.3. Throw that in your z-score. That's 48 minus 67.3, 10 over 10.3. So we put that in our z-score form. That gives us -1.87. So it's -1.87 standard deviations lower than the mean or lower than the average. So then you ask yourself, is this unusual? The answer is no, because remember, it has to be either greater than 2 or less than -2. And so notice it's not less than -2, so it's not unusual. All right, so that's the end of the packet. Let me know if you have any questions.